All right. Good morning, everybody. Welcome to our UI Assist webinar. We delayed it a week because Distribute Tech was supposed to be last week, but we really appreciate our colleagues from Burns and McDonald for giving an overview of the report that they've written and just providing some insights into alternative communication technologies and cybersecurity as we look at a DER-rich systems. So now I'm going to turn it over to Francisco to get the seminar going. So thanks, Francisco.
Okay, yep. Thank you, Dr. Schultz. So good morning, good afternoon, or good evening to all the attendees today. My name is Francisco Neto. I work for Burns McDonnell, and I will be the mediator today and give a quick introduction to this presentation related to our report on alternative communication technologies and cybersecurity in DER-rich systems. As a reminder, this report is available in the project SharePoint under the theme 5 deliverables. So make sure to check it out. And before we start, I would just like to remind everyone to please mute their mics if you're not talking. And if you have any questions before the end of the presentation, please post them in the chat and I will relay them to the presenters at the earliest opportunity. So let's start with an introduction of our 4 presenters today. Sami Patton is an electrical engineer specializing in telecommunications and network engineering design. Mr. Patton's experience includes producing and reviewing technical and physical designs for MPLS deployments, evaluating diverse substation topologies, and rapid testing and deployment of network solutions. Our second presenter today is Nick Moser. He's an electrical engineer working on networks, integration, and automation projects. His experience includes wide area networking design and implementation with multi-protocol label switching, MPLS, design of Wi-Fi networks in densely populated airports, distributed antenna systems, DAS, cellular backup routers, and documentation of fiber optic outside plants using GIS. Our third presenter today, Dan Bayouth, is the project director for networks in the Networks Integration and Automation Department at Burns McDonnell. He specializes in telecommunications and network engineering for critical infrastructure. His experience includes MPLS, private LTE, substation IEC 61850, DWDM, and SONET network design, construction, integration, and operations. He has served as project manager and senior architect for the design and construction of multiple utility-wide network installations. And finally, our fourth presenter today, John Biasi, is an associate cybersecurity consultant with Burns & McDonnell. He is also an adjunct professor at the Oklahoma State University Institute of Technology. He received his Master's of Business Administration degree with a concentration in cybersecurity management and his Bachelor of Science degree in Information Technology from Excelsior College in Albany, New York. As a senior consultant for governance, risk, cybersecurity, and compliance at Burns & McDonnell, his primary focus is to protect critical infrastructure by focusing on risk management in the context of cybersecurity, physical security, and regulatory compliance. He is an active participant in the NERC Security Integration and Technology Enablement Subcommittee, CITES, Smart Electric Power Alliance, SEPA, and the Utilities Technology Council, UTC, focused on grid modernization, cybersecurity, and compliance. Now, just FYI, their contact information is there, so feel free to reach out. Now let's move on to our agenda. We will start with a quick introduction of the report. Then we will talk about each of the three main sections discussing communications and networking options, and then cybersecurity attacks and available measures. And then we'll finally wrap up with questions from the audience. So as an introduction to our webinar today, this report came together as a way to outline in more detail the different options you might have for communications and networking when dealing with a grid with high DER penetration. But we didn't want to simply define what these options are. We also wanted to discuss some of their properties and characteristics when immersed in a DER-rich grid. And then for cybersecurity, it really wraps around these two topics, and that's why we speak of it in more broad terms than the first two. Assessing potential cybersecurity threats and how to respond have well-documented guidances and that outline the process from beginning to end. And some of these guidances will be discussed as part of this presentation as we reference the existing documentation. But for a full description of all the guidances in the framework that we'll discuss, please refer to our actual report. I will now hand it off to Sammy and Nick, who will start with their discussion on the communication section.
Awesome. Thanks, Francisco. Welcome, everybody. So in this section, as Francisco mentioned, we're going to really kind of take a deep dive into what a DER-rich communication system or network actually looks like. So these networks provide kind of the fundamental infrastructure for information transfer in a DER-rich grid. So just to give you an idea, the architecture for such a network varies widely, but the below diagram kind of gives us a little bit of idea of what such a system could look like. Obviously, these are very interchangeable, and you don't need every single thing that you see in this diagram, but let me just walk through it really quickly here. So the meters and cellular capable devices, these are the things that you see kind of on the bottom left in the orange. These are devices that provide supervisory control and data acquisition. So that's SCADA as an acronym. I'm sure many of you are familiar with, but these devices provide data to SCADA systems, which then communicate with a distribution management system at the top left there. So the DMS there, that could reside typically at the utility head end somewhere in the data center or something like that. Devices like battery banks, generators, renewables in the green there at the bottom. So these are devices that can typically communicate with a microgrid controller. So if you have a huge set of batteries, an entire site dedicated to renewable, a wind farm or something like that, there will be a microgrid controller there that'll talk to potentially a local distributed energy resource management system, DERMS, and then up to a DERMS master, or potentially just go straight to a DERMS master to the DMS. Like I said, these networks are pretty flexible. Home and commercial networks kind of follow a similar structure to some of the renewables and things like that I was just discussing. And then another kind of important thing to note here is that when discussing backhaul, which we'll mention here in a couple slides, it's often referred to as the path back to the DMS or to the DERMS master, something like that. So typically not used within a site, and that'll kind of influence the discussion on some of the technologies that we have in the upcoming slides. Next slides, please. So, with such a large number of different technologies available for use, these in these communication networks, we need a certain metrics to be able to compare their usefulness and where to apply them. So data rate is one of the big ones. This is the measure of information transfer between 2 points over time, usually in the scale of bits per second. I'm sure everyone's familiar with their internet speed in megabits or maybe gigabits per second, who knows. Typically the DR data is not particularly intensive, and something in the bits per second or kilobits per second range is sufficient for total data transfer. In fact, the U.S. Department of Energy estimates that 100 or 10 to 100 kilobits per second is typically enough to carry information from a home to a central aggregation point. So this would be something like a utility facility or to a utility pole somewhere or something like that. Quality of service, QoS, often referred to. This is typically used to manage the quality of a communication link. These are parameters like packet loss, data prioritization, jitter, uptime, all those things kind of come together to determine a link's quality of service. And it's often really a function of specific technologies and protocols being used. So it's not necessarily that, if you use fiber, you're going to get better quality of service. There are a lot of other things at play, which we'll get into later. And then latency is the delay required in the transfer of data. So no communication system is instantaneous. So things like propagation time, processing time, queuing, within a router or something like that. These each add time to the transfer. And DERs aren't typically considered critical communications, so the higher latencies are generally acceptable in these instances. Again, the US DOE says that 2 to 15 seconds isn't outrageous for DERs, whereas just for some context, in a protection system, we would hope for less than 20 milliseconds. So quite a big difference there in the range of latencies. When comparing data rate and latency, it kind of seems like on the surface they might be similar. It's kind of helpful to think of it kind of like a water hose, except instead of water, obviously the medium being transported is data. The data rate, or it's often referred to as throughput, is the data you can think of it as kind of the rate of water flowing through the pipe, whereas the latency will be kind of the time it takes to travel through that tube. So there's another kind of metric, bandwidth. If you want to get into that, bandwidth would be kind of like how wide that pipe is. So next slide, please. Awesome. So we've got a couple different types of communication. Wired or wireless is really kind of an easy way to break it down. And the distinction between the two is really made in terms of, what your location is, your device limitations, financial resources. These all come together to kind of decide whether wired or wireless technologies are right for your system. So wired technologies, these are, everyone is well aware consist of a physical link between two devices. Wired technology has been around for a long time. Wide adaptability between legacy and more contemporary devices. So we're just going to dive into a couple of these here. Twisted pair. Francisco, if you don't mind doing one more click, just give some idea. Yeah, so twisted pair, this is commonly used and available for many decades. Twisted pair cables consist of copper conductors, typically with plastic insulation, twisted together and then formed into a cable. Obviously, an example we're all very familiar with is the classic blue Ethernet cable. The most recent specifications of twisted pair cables, Cat 6, 7 even, we can support gigabit speeds. The most require far less. And then obviously, as I mentioned previously, especially in DER-rich or for DR devices, we typically don't need that sort of those sorts of speeds. So latency, again, is kind of dependent on the underlying technology as well as kind of the number of hops and general congestion in the network, but it can be very low for twisted pair cables. And although twisted pair cables are cheap and they're commonly available, they do suffer from some common issues that you see from any sort of physical media. Cables can break. They're susceptible to lightning and other faults. And if there is a fault, it becomes difficult to kind of pinpoint exactly where that failure occurred. So another kind of wired media is fiber optic cables. So this is a little bit more recent, but you'd be remiss to think that these are new. Fiber optics have been around for, again, many, many decades. I think since the 60s or something like that. But these are essentially media where light is transmitted down the length of an extremely thin glass fiber. So owing to kind of the underlying physics, these fiber optics can provide extremely long distance transmission, tens of kilometers, and data transfer at extremely high data rates, because there's just little loss, again, due to the underlying physics. These metrics are typically influenced heavily by the technology being used. So, kind of a fun example is our transatlantic fiber optic cables. So obviously these are going thousands and thousands of miles undersea between Europe and the US or North America. And they're using, very powerful optics and things like that. So it's possible to get some extreme performance out of these this medium. So in microgrids, fibers typically, this serves as a backhaul for some of these stated reasons. In home DER applications, it's a bit expensive or certainly more expensive than traditional, Ethernet cables, Cat5, Cat6, and then the additional performance benefits are typically unnecessary, especially if you're using it at home. You don't need to be running fiber everywhere. And then the final one that I really wanted to touch on here is power line communications, PLC. PLC uses these coupling capacitors to tie communication signals onto existing power cabling. So as such, it doesn't really need new cable runs, which is helpful between the endpoints. So implementation costs can be quite low, but data rates are also sufficient. They get up to 200, megabits per second. So certainly not as fast as twisted pair fiber optics, but again, kind of unnecessary for DER applications. And then the same physical issues are kind of apparent that we talked about with twisted pair. And there's also an added significant susceptibility to EM interference, for motors, radios, power supplies, things like that, because these power lines are typically not shielded. So next slide, please. I'm going to hand it off to Nick to talk about kind of the wireless options that are available.
Yeah, thank you, Sammy. Appreciate it. So piggybacking off of the wired options, I think wireless is something that most of us are familiar with as well. The first example I've got on here is Wi-Fi. So that's the IEEE standard 802.11. And I think we all know that, this is scalable and it's low cost. You can basically buy these off the shelf and implement it in a home or business. And it pretty much works up to the standard, and you can get pretty good data rates out of these. In fact, the latest standard for Wi-Fi 6 or Wi-Fi 6E even, the theoretical data rates are now up to the gigabits per second range, even 9, 10 gigabits per second. Now, that's theoretical. Are you really going to get that? Probably not. But is it needed for especially a DER application? Arguably no, really, unless you're doing some kind of virtual reality or gaming or something like that in your DER, probably isn't a place for a data rate that high. However, it is very standardized, so there is something to be said for having a product that that works and being able to buy something off the shelf and implement it. One thing with Wi-Fi is the latency does vary dramatically with increasing network load. So depending on how much you put on a certain Wi-Fi link, the latency could get too long. You just have to make sure to check that during, a design of the DER. What do we actually need as far as data rates, though, in a DER. I think, Sammy touched on this a little bit, but if you think about the kind of data that's coming back into a control center or even within certain devices in a DER, it's just ons and offs, zeros and ones for the most part. You might also have some digital values, maybe meters or measuring kilowatt hours, or instantaneous power. But these are just small digital values that are transmitted maybe 3 to 5 seconds apart. And so, really, at the end of the day, there isn't a whole lot of data that needs to be transferred. Looking at some other options that we have here, like Zigbee, this is a pretty low cost technology that's often used in personal area networks. For example, in a home energy monitoring system. They're low cost because they're low power, so they don't output very much, and in turn, that means that there's not a lot of distance you can get between these. It's about 100 meters or so, but because it's low power, you also get a long battery life. So there's a little bit of a trade-off here, and depending on the type of application, this is where you might consider, Zigbee versus Wi-Fi. Another advantage of Zigbee is you can use a mesh network and increase the distance. So there's actually an example here of a mesh network on the right. So the product that's shown there is a common MAS system, which is what we call multiple address system. So this is shown in a mesh form, and this is just another wireless technology which is often used to reach substations in a utilities network that are a distance away from a control center, and perhaps it doesn't make sense to run a twisted pair or a fiber optic cable or even rent, communications from a telephone company to some kind of remote substation. So these radios in a mesh form can communicate with each other and then in turn communicate back to maybe a microwave tower or another way to get to the utilities control center. And these are often used up to tens of miles. I think we got up to 50 miles on there. And that's really highly dependent on the terrain and where your antennas are mounted and such. But in any case, this is often an application that we see in distribution SCADA environments to reach the energy management system. If we could go on to the next slide, please, we'll talk about cellular systems. So again, something that I think everybody's familiar with. What you might not know is cellular does come in different flavors. So I think we've all heard 4G, 5G, LTE. That's just a matter of, standards versus marketing. So LTE really is the standard, and it's very highly standardized. So this means that you can go pick a user equipment, which is just a in-device, say, for example, a cell modem that's mounted on a recloser pole or in a DER that can communicate back to the head end. And this device, because it has the LTE standard, is going to conform and behave in a way that can be interoperable with your other equipment on the network. So in other words, you're not just stuck with one type of vendor as you might be if you got, say, an MAS radio or a Zigbee radio. So cellular does come in public form, which I think we're familiar with, and then private as well. So we're seeing this in the utility space. A lot of utilities looking at private LTE networks as an option to expand and scale their communications to many different parts out in the distribution grid. With LTE and with cellular, there's also no line of sight requirement. So you can basically reach more locations than you could before. And there's ultra low latency applications. So especially with 5G, that's what a lot of 5G is looking into, is how can we reach the endpoint faster and with higher data rates. One example of this, as you can see in the little diagram here, might be like a solar field reaching the control center. On the same network, though, you can also have, say, a utility worker sitting in a bucket truck, and they're communicating back with their other colleagues out working on different parts of the grid, or maybe back to the control center. So cellular is something that we've seen implemented for many years, of course, several decades, especially in the utility space, and even in DERs to reach that last mile where it just doesn't make sense to come in with some other type of communications. If we go on to the next slide, we'll talk about how to compare these. So now that we've laid out what kind of options we have between wired and wireless communications, and we also have the metrics to stand these up against each other, how do they stack up? So on this chart, you see two different charts here. So the top one is an intra DER chart. So this is between or within the DER. For example, this could be like a home area network or a microgrid. So looking at the data rates and our typical latencies here, which keep in mind they can vary highly. So it depends very much on the environment and how much is on the network and types of antennas and such. So just keep in mind that these are typical values. But essentially with short distances, if you want good performance, you're pretty much always safe with a wired solution. Wireless will allow you to expand, so you can get to more further out parts of your grid. And most applications won't have a problem using wireless. But if you really need good solid communications and you're within a short distance, then twisted pair would definitely be the way to go. If we look at the second chart, which is grid to DER, so this is going to be over longer distances. Like Sammy mentioned, the backhaul type of solution. So fiber optics, the PLC, MAS, and then cellular, which we hit on, of course. So looking at this, obviously fiber is super hard to beat. We do have 10 to 30 milliseconds here. Keep in mind that's probably more for like a switched network where there is some processing involved. If you look at the actual end-to-end on a fiber strand, light on fiber cables essentially travels at 31% slower than the speed of light. So that's basically around 200,000 kilometers per second. So if you want to look at it from a physical standpoint, that's your latency. We add latency on top of that when we start to introduce devices that have to process that data. But nonetheless, fiber is probably going to be gold if it makes sense. It doesn't always make economic sense. And so that's why you might look at something like a PLC or MAS. And in fact, for our low data rate and low latency applications, those happen to make more sense in many cases. And then cellular, of course, just being widespread and available, that's another option to consider. So takeaway from here is there's a lot of tools in the toolbox, and it really depends on what type of application you're going to be using and looking at before you can decide which technology to implement. So on the next slide is just a brief comparison to see when we compare against data rate and latency. So this is intra DER within the same microgrid. Right here, you can see twisted pair, of course, highest data rate and the lowest latency. But on the other hand, you've got Zigbee, which is low data rate and higher latency, however, may be very tolerable for what you're doing. Of course, you wouldn't want to use a Zigbee for a teleprotection type of application. As Sammy touched on, that's typically you want less than 20 milliseconds. And that's really because in alternating current at 60 hertz, one cycle is about 16 to 17 milliseconds. And so it's really important to consider how many cycles can pass before your communication needs to reach the other end. Now, if you think about what I said earlier about just getting status points and metering values, then it's not very important because we're talking seconds instead of milliseconds. And Zigbee might be a very applicable application to what you're doing. On the next slide is grid to DER. So the other example over the long distances, going from the microgrid back to a control center or a head end. So again, these are the backhaul options. Of course, fiber is going to be king for the high data rate. And, we talked about latency as well. But like I mentioned before, MAS, even though it's the lower data rate on here, and arguably cellular could even be lower depending on signal strength and of course the application. Those options are still very much seen and used in the microgrids that we see today. So just in summary here, the wired and wireless technologies both connect devices within the same microgrids and within DERs, and also from DERs to the rest of the grid and the head end. The important things to consider when trying to select an application or technology for your application are latency, data rate, and quality of service. It's important to consider all of these things specific to the environment and the application that you're working with. And with that, we'll hand it off to Dan to give us a little bit more.
Dan, before you start, we have a quick question for Nick. Nick, Gary's asking, where does data traffic control come into play? Is it a typical strategy to prioritize traffic?
Yeah, that's a great question. So it is very common to do this in a utility network. The reason, for example, as we touched on, there are some applications that are definitely considered critical communications. So, a relay channel between two substations that is responsible for tripping a breaker if there's a fault on a line is arguably more important than somebody sitting in their bucket truck on the Wi-Fi checking their email. We would want the communications for the relay channel to go in first, and that would happen so fast probably that the person, watching YouTube or on their email, they probably wouldn't even notice. And we just want to make sure that we can prioritize what's actually needed. And so, yeah, we often see this. It's probably going to be more so on the grid to DER type of communications. So that's that long haul type of communication. Within the same microgrid, you're typically not doing those same types of critical communications, the teleprotection application. And so may not see it as much there.
Perfect. Thank you. All right. On with Dan.
Hello, Dan Bayouth, and so that was kind of a lead in through different communication protocols and methods, and I'm going to give you a little background of what is driving utility communications, why is all of this relevant. And in the 1950s, in the U.S., the first private communication systems rolled out, as well as using public carrier for some applications as well. At the time, it was AT&T because they were the public carrier. But in the 1950s, an application that the utility needed that really wasn't provided by anyone else was wide area two-way radio, walkie-talkies, land mobile radio. It goes by several different names, but this was not an application you could go get anywhere. So they started building private communication systems so that they had a method for dispatching for outages, repair work, whatever they needed without having to go to a phone for those orders. So these two-way radio systems were kind of the initial private communication system, in addition to using public carrier, say AT&T, and at the time this would be just analog lines. So, 2-wire or 4-wire voice frequency, a phone line, to put it simply. The carriers were able to provide Class A high, or low repair time, high reliability circuits that could carry SCADA, which is the supervisory control and data acquisition. This is control for the transmission system. So we didn't have to have a person who reported to a substation and stayed there and did shift work and really just a manned facility 24/7 to do switching orders. You do remote control of the station, as well as teleprotection, the ability to trip a high voltage line off in an emergency. So we have the public system with these critical control functions, and then a private system kind of coming up alongside it with the two-way radio. However, as things have evolved, today's multiple carriers look very different than the AT&T of the 1950s, 60s, 70s, in that they're looking to abandon all of these copper lines. They're looking to, the businesses are diverging. The business need of a modern carrier is providing high-speed wireless for your cell phone. It is providing some data services over fiber, but largely the need to provide mission critical leased circuits is not a core part of the business of a public carrier. So when AT&T was a monopoly in the US, they measured their success as a monopoly by reliability. Similar to how an electric utility does today. There aren't competing electric utilities in a service territory. Their measure of success is how reliable, how much of the time they keep the lights on. Well, when AT&T was the only phone company, that's how they measured their success, is look how reliable we are. Well, that's changed. There's plenty of competition in, where I can get cellular service, where I can get internet service providers for the most part. There is competition now. So now they're measuring success in how many customers they have and that often is a race to get a low price that attracts customers. The reliability aspect still needs to be there, but not to the degree it once was, and not to the degree electric utilities need their communication for grid control. So if the lights are on, they need grid control. The FCC allows certain types of maintenance that would be disruptive during the day to occur at like 2 a.m. There's a window at night where the public carriers can do outage work. You still need electricity at those times. So the utility needs to control the maintenance cycles of the communications as they become more and more critical to the operation of the grid. So, the transmission applications, these are the early drivers. I need remote access to the site. I need to get fault recorder data. I have SCADA, teleprotection, and phaser measurement units have been becoming more popular. They're not mission critical, I wouldn't say today for our many utilities, but these are more and more data I need to get out of the transmission system. Okay, next slide, please. So these wide area networks in the 1980s started putting fiber optic cables in. Electric utilities own lots of vertical infrastructure, the wood poles, the transmission structures, and that was a ready pathway for fiber optic cables to start carrying some of these circuits they needed, often for the two-way radio system. So I build microwave rings, I build fiber optic cables. I can start utilizing these for my two-way radio system, but also I can start migrating some of my other, I have a fiber cable, it's got plenty of capacity. Why don't I use it for SCADA? So in the 1990s, we start to see high speed, at the time, very high speed networks, 100+ megabit private fiber optic networks they could start running. So in the 90s, it was, well, we have all this fiber, and the adding a network on top of that is an incremental cost, but we can also converge all of our applications onto a common infrastructure. And then in the 1990s, a lot of this was serial traffic, like RS-232 serial, a lot of 2 and 4 wire voice frequency circuits, and some DS1s for the land mobile radio system. But these were the kind of things we saw on the SONET networks, and that they all fit together very well. Well, as that technology aged, and a critical moment in 2009 was an infrastructure bill was passed that included money for smart grid. Well, in 2009, the world of Ethernet and IP was starting to take over, and a lot of these new applications were not what we now would easily consider legacy protocols. serial, and voice. These are not just IP applications, and it kind of drove the need to, SONET networks do not scale very well when you start adding asynchronous things like Ethernet and IP that need large bursts of traffic and actually do very well at sharing a medium. So 2010 kind of starts the US utility migration away from SONET and towards carrier technologies, current carrier technologies like MPLS and carrier Ethernet that scale very well with IP applications. And this is, as previously discussed, QoS. This is where we have to look at, now I'm prioritizing, in SONET, I was time division multiplexing. I'm sharing bandwidth over time, and everybody gets a guaranteed slot. As I move to an Ethernet IP world, things need to talk when they need to talk, and I can share this a lot smarter using what we use every day, and we don't really think about it. Ethernet IP packet networks use statistical multiplexing, which is just the concept that not everything needs to talk at the same time. And when lots of things need to talk at once, we can prioritize that data. So we're a lot better at sharing the capacity of the network than we used to be. Next slide.
Before we proceed, then we have a question here.
Okay.
In cases where utilities use cellular networks, they mostly use lease lines provided by AT&T or Verizon or others, right? And if so, who takes care of the networking part, like configuring MPLS layer 2, layer 3 VPNs, or IPsec? Is it completely taken care by cellular service providers?
So I want to make sure I'm answering the question like as related to the slide. When I say MPLS on this slide, it is related to a private network owned and operated by the utility. They control it. It is separate from the any public service. There's no AT&T involved, nobody. They control 100% of that. And then I would also say today, a utility using cellular service, for the most part, is using a leased service from a carrier. The carrier would then, there would be a handoff point where you'd get a leased gigabit, whatever type of connection to the carrier, and they would drop your traffic off. So on the private network side, that's all the utility. They're setting up any layer 2, layer 3 VPNs. That's all internal to them. On the public side, when we get to cellular, for the most part today, that connection starts on a carrier network and ends in on the public side and ends on the private side. And I'll answer the rest of your question here in a minute. So let's go to the next slide.
Sounds good.
Substation LAN, briefly touched on this, but really inside a transmission or distribution station, we can start reducing a lot of the copper cabling. We can get more intelligent communication within the site, and also sampled values. In other words, digital signals. So we get a current reading in the yard that gets translated into a data value that's pulled into the substation. So I'm moving all that high voltage, high current stuff, and I'm where that used to come into the station to read it, pushing that back out to the station to kind of isolate my electronics more than they used to be. So what's really happening for the communication side is I need highest reliability, more fault tolerance in the LAN. So that's kind of driving. This is not the most complex part. Today things like PRP, HSR, standards-based protocols for zero hit, zero downtime substation LAN is really what's required. And I think that's mostly become a solved problem for if you built a brand new substation from the ground up, you could easily accommodate all of this. A little more common Europe and Asia than it is in the US today, but these are the substation LAN has evolved into being very reliant on high availability Ethernet. So go ahead and go to the next one. I think, yeah, here we go. So the field area network, this gets back to your question about cellular. The field area network So what's driving the evolution of the field area network and distributed energy? We got DERs, microgrids, we have customer generation, the electrification of transportation. So we have new high demand on the distribution system that wasn't there. Situational awareness, we have more sensors. The utility needs to be more aware of what is going on in the distribution system than they ever have, because there's effectively a two-way power flow. I start putting solar panels on my house, I can feed some of that back into the grid. That's entirely new. This was never a two-way street. When the grid was designed, it was not a two-way street. So as we see electric vehicle charging putting big demands, and then solar installations adding the two-way power flow, and as well as energy storage for large batteries, things have changed, and the utility today needs more visibility and eventually control of what is going on in the distribution system. So this is a big driver for changes in the field area network. So let's go to the next one. So pretty much what I just said, we've got DERs, cars, controllable distribution devices. So this started with the term smart grid in 2009, but has only gotten more important that we can control, automated sectionalizing and reclosing, volt var control, understanding where faults are more accurately. As we get more COM, we can get better visibility into the grid, not only for outages, but how the power is flowing and where it's coming from. So let's go to the next one. So here's your technology roadmap. In the 2010s, we had mesh networks. So the big smart grid grants fed a lot of mesh networks, and we found in the end, this was supposed to be an amazing way to get network into the home and all sorts of great new capabilities. And what really 10, 12 years later, what kind of shook out as the best application for mesh networking was AMI, automated meter reading, and automated disconnect are two really big applications. And the disconnect actual benefit to the customer is the utility can get your power back on without a human visiting your site. So when you get behind on your bill, you pay your bill, they can switch it back on, let's just say within an hour versus a couple days to dispatch a person to go hook your meter back up. So the mesh networks were great for the automated meters. The downside is low capacity and high latency. So as we need more real-time visibility into the grid, the mesh networks don't scale very well, because really to get capacity in a mesh, I have to go add takeout points into the mesh out in the middle to reduce the number of hops things have to go. Now I effectively cannot increase channel size. Frequencies these use are unlicensed. I'm restricted in how I'm allowed to use the RF frequencies for mesh networks. And by and large, there is a reason your cell phone is not on a mesh network. The architecture just doesn't really scale and perform the way it needs to. It's very complicated. So we end up with point to multi-point is more optimal, because really every tower or every takeout point is a path to a high-speed network and a way to get traffic out. Ultimately, what we're trying to do is get traffic from the end device onto a high-speed network, and then it can go where it needs to very quickly. These narrowband systems were lower cost, but low capacity. Latency was better than a mesh because it's always a single hop for the most part. Unlicensed or licensed, you can get very long range out of the licensed frequencies, like miles and miles. Down at 200 megahertz, you can get tens of miles, 20 miles away from a tower site. But narrowband, if we have a narrow RF channel, you're always capacity constrained, and data needs of anything in the field are never going down. So we go to leased cellular. The networks are already everywhere. effectively you have near ubiquitous coverage in the US. Not always true, but for the most part, where you have a lot of distribution, meaning people, you have cellular coverage. However, there is no guarantee of service or repair time. There can be planned maintenance in the middle of the night, whenever we need to, whenever the owner of the cellular network needs to do their maintenance. Then came kind of WiMAX, a little more broadband point to multi-point, high capacity. They controlled everything. However, frequencies available were very low range, which led to the need to build a lot of infrastructure to serve the applications. Today, private 4G, private LTE is something utilities are looking into as, the world standard, standardized on Ethernet and IP. The utilities followed suit. The world has standardized on 4G, LTE, the 3GPP protocols. That's the world standard. That's where the device costs are low. That is where the infrastructure, the radio networks, all of that's been well established. High capacity, low latency. They can guarantee their own service if they own the network, and then build the coverage as needed to cover their electric grid. They don't have to cover everything on Earth to get to every home and everything. They need to cover their assets so they have communication. So that's really driving the look at private LTE, is controlling repair times, controlling the communications end to end. As communications become more vital to electric system operations, the utilities need to build a system that is just as reliable as the electric grid. Public carriers are building a system that has ubiquitous coverage to cover as many people as possible. However, they are willing to tolerate some outages as a trade-off for less infrastructure, less cost that they as a business won't necessarily see the benefit of over time. I think that is my last slide. Go ahead and go to the next one. Yep. So I will hand off to John.
All right. Thank you, Dan.
All right, thanks. Hi, everybody. This is John Biasi. So I'm going to talk a little bit about cybersecurity, and I know we're kind of running short on time, so I'm going to kind of fly through a few of these slides just to get kind of the points here. But just kind of on the overview here, the intent for cybersecurity from a distribution perspective is to fail useful, where in other applications it might be okay to disconnect or disable a connection because you don't want the attack to continue. There's some consequences to doing that on the distribution grid. So the goal is to kind of take away some of the remote control and access to keep it stable and functional without necessarily shutting things down. On the distribution side of things, you don't have to have the same level of mandatory cybersecurity requirements, at least in North America, related to NERC-CIP. That typically is at the generation and transmission level. So once you get down to distribution, those standards don't apply. But you tend to have some more local and state type of requirements and more voluntary cybersecurity practices that are followed for distribution grid. Next slide. All right, so just in this slide, just talking about traditional cybersecurity measures. If you're thinking about some of the basics that you would implement when you're trying to build out your cybersecurity strategy, here are a couple things that kind of come up as the kind of the heavy hitters. In this environment, one thing we're worried about is that these things have a cost, right? Not just a cost in terms of dollars, more in terms of things like latency and processing overhead and things like that, like encryption. If you go for the highest levels of encryption, you have some processing and memory and bandwidth constraints that would affect that. Similarly with firewalls, you have, if you add in a firewall, it adds latency at that hop where everything has to go through, as well as the fact that the more intensive, like next generation firewall analysis and behavior type of activities you can put into those firewalls, they will have a higher cost in terms of latency. All right, next slide. So as this relates to the grid, I mean, we're talking about a couple of different areas here that relate to some of the kind of the standard things we're concerned about here. We talked a little bit about AMI previously. this started out as more of a, hey, shut off meters, turn them on, things like that. It is evolving. There's a lot more in response and other areas where it's starting to become more useful, more important. It also has a cybersecurity implication in the fact that, if you have the ability to shut off someone's meter or turn it back on, what happens if that capability falls into the wrong hands? So you have to worry about the ability to access those types of functions. Other things like distribution automation. Similarly, you're looking at moving your connections between different substations, moving allowing for something to be switched from one substation to another. These types of things all have benefits to the utility, but they also have some real concerns in terms of what they could be, how they can be misused. Skipping ahead to the electric vehicle piece of it, now we have things where there as Dan had mentioned earlier, this two-way street. You have things where things want to talk back and things want to get information from the grid. Potentially, you can pull power from a charging EV if you need it for demand response, things like that. These types of things increase the level of complexity of the communications. Now we're not just reading a meter, seeing what amount of power is being utilized. We're also coordinating and potentially issuing different changes based on the data we get back. The ability to have that information be reliable and trustworthy is very important from a cybersecurity perspective. All right, next slide. So, some of the things where this comes into play is certain attack techniques, things like phishing, right? A phishing attack is an area where you definitely have an issue of potential compromise of privileged user credentials that could have an impact if it's on somebody who has access to some of these environments. Supply chain is a kind of a big newsworthy item at this point, because a lot of these components are assembled or worked on, or pieces of them come from different places in the world. We don't always have the ability to vet all those components, both from a physical hardware perspective as well as from the software. A lot of things tie back to open source projects or other, companies borrow modules from other software vendors, and they don't always have the ability to talk back to those vendors and see how they are properly securing their code. And then just internet accessible devices in general. I mean, a lot of us have things like Nest thermostats and all these other things that that are accessible, and they may tie into the AMI infrastructure, as well as I wish this wasn't the case, but unfortunately, in some environments, there are more important devices that are put on the grid that shouldn't be. If you go to there's a very good scanning tool called Shodan, and they have a visualization called ICS Radar, which shows you where in the world you can see ICS protocols directly connected to the internet. So what that implies is that there are at least some utilities out there who are putting some of their devices straight on the internet with no protection in front of them. You can even scan for things like serial numbers and models and firmware versions and things like that for some of these devices, which is a little scary. So things like that are a real issue for this type of environment. All right, next slide. So impact, all the things we talked about earlier, right? Anything related to resiliency and reliability, and having the ability to keep the grid running. Those types of impacts are a real concern from a cybersecurity perspective, because these communication pathways are not always, to some of the earlier slides, was not necessarily built to be 100% resilient and reliable all the time. So having the ability to keep them that way requires some level of cybersecurity controls around it. All right, next slide. Okay, so the intent of the next couple of slides is just to kind of introduce this cybersecurity framework. The idea of the framework is that it is a standard kind of a vendor neutral cybersecurity guideline that you can use to apply standard risk management techniques to any industry. And there are some very energy sector specific guidance on it, but it is meant to apply to critical infrastructure in general. It allows for some decisions to be made from a risk management perspective. There are three components to it. There's a core, there are which basically is the framework and guidance. There are some profiles that are specific organizational requirements, and then there's implementation tiers, which is more of a measure of how effectively it's working. All right, next slide. So there are 5 components to the framework core, which is these things listed here, which is identify, protect, detect, respond, and recover. It covers the full range of when figuring out what you need to protect at the identify stage, all the way to how you respond to an attack and how you recover from such an attack. So it's meant to cover all of those levels. I see that there's a question: is cybersecurity the same for power system and other sectors? For example, the financial sector. I mean, in many cases it is. There's a lot of cybersecurity techniques and practices that apply across the board. Where it tends to differ is in the implementation. So, I mean, one example, like on the previous slide, one of the kind of basic cybersecurity things you want to do is patching, right? Patching is important because it keeps your systems up to date with the most recent version of the code, that anything that might have been found to have a bug in it or some kind of a potential for compromise has been corrected. So you keep that software or firmware up to date, and it keeps you away from potential attackers who could exploit that vulnerability, right? But it's sometimes there's a trade-off between taking the system offline to patch it and then having the system available for use, right? So in some cases, the threat of a device that is protected by multiple layers of security might outweigh the need to take it offline, right? If the loss of availability is a more critical concern in the electric utility space, whereas in the financial space, disclosure of information might be the priority, right? So they're much more worried about your financial records getting out, whereas on the utility side of things, we're much more worried about the availability piece. Not that those other things aren't a factor as well, but there's sort of a different balancing in the equation sometimes. All right, next slide. So basically, yeah, the framework core just describes the outcomes that is understandable by everyone. That's meant to be a kind of a universal way to do this, right? It's not meant to be that we're going to do it differently from sector to sector, but your results will vary based on your priorities, right? So these types of things will play a factor in what you end up using this framework to do. All right, next slide. Okay, so here's just an example. So in this cybersecurity framework, the category of identify, one of the things in there is related to asset management. So basically, you're looking at the need to identify the assets that you're going to want to protect. And this is an example of a guidance that you can use to figure out what those systems are and how they work, and kind of build that into a step-by-step process to go ahead and identify what things you want to focus on for your priorities towards cybersecurity. So we have this sort of thing, and in the report for this, we have this laid out for every framework item in there. So you can look at that at some point and see kind of the guidance for each of these categories. But this is sort of an example of what one of those looks like. And I believe that's probably my last slide. Yeah. So I know I had to run through that real quick. If you have any questions, feel free to ask, or my contact information was on the slides as well if you need to reach out. But thank you very much.
Okay, thank you to all of our 4 presenters today. So I'll open the mic to any questions that the audience might have. I know we are a little bit over, but if you have a few minutes, feel free to send some questions.
Yeah, so I see one question in here, and we can go over, and those people, we're recording this, so people have to get off, they can come back and see it. So what is cybersecurity oh, you already talked about that one.
Yeah, so, we answered that one.
Other questions? Sorry, I just scrolled up, so I thought it was a new one.
Oh, no worries. Okay, I'll just leave off with our contact info here. Feel free to reach out if there's any other questions. And thank you everyone for joining today. And thank you again to our 4 presenters from Burns & McDonnell.
Yeah,
Have a
thank
good
you
day.
very much. That was very comprehensive. We appreciate it.
Thank you.
Thank you.